In this video, we'll look at independent sample difference of means testing. What that means is we're going to be comparing the means of two different groups and seeing whether or not they're statistically equivalent. For example, we might look at GPAs as our dependent variable and wonder whether or not men and women have different GPAs. We can do this by taking a sample of men, taking a sample of women, and calculating the mean for both groups. Through a difference of means test, we can compare whether or not those means are statistically equivalent. In general, an independent sample difference of means test is looking at whether or not those two groups are drawn from the same population. For instance, the null hypothesis in an independent sample difference of means test would be that the GPA for men is equivalent to the GPA for women. That is, even if we separate men and women into two different groups, the GPA averages will be the same for both groups because men and women were drawn from the same distribution of GPA in the population. Alternatively, we may observe a difference in GPA between men and women because those groups are fundamentally different. That is, that a single population mean does not accurately represent men and women, and therefore the means are different in our sample observations or our sample groups. The alternative implication would be that the population mean for men and the population mean for women is actually different, which is why we're observing differences of means within our individual groups. This makes a little bit more sense in an illustration, so let's look at that illustration now.
Alright, so let's try to visualize how an independent sample's difference of means test works. So once again, we start with a null and alternative hypothesis. The null hypothesis is that the mean of group 1, which I've noted here is x bar 1, is equivalent to the mean of group 2, which is x bar 2. Or the other way you can phrase the null hypothesis is that if you take the difference of means between x bar 1 and x bar 2, that difference will be 0. And obviously, if the means are the same, the difference between the means will be 0. The alternative hypothesis, of course, is that the means of the two samples are not equal. That is, x bar 1 is not equal to x bar 2. Or that if you took the difference of means x bar 1 minus x bar 2, the difference would be not 0, either less than 0 or greater than 0. Alright, so the way I like to think about the null and alternative hypotheses for independent samples difference of means test is to kind of start with the recognition that we're always going to see the difference of means be something other than 0. It's going to be a rare case where the means will exactly be equal to each other and you'll get a 0 outcome. So the real question is whether or not the difference in means is driven by random sampling error from the same population. That would be if the null hypothesis were true, or if the difference of means that we're observing is a function of the alternative hypothesis being true, where the groups are actually different in reality and in the population. So let's say, for example, that we separated students by gender and we were looking at their average GPA. So here, let's say we put a sample of men into group 1 and we put a sample of women into group 2. Now, if there is no real difference in GPA across gender, then really GPA is drawn on the same population. That is, there are going to be a lot of students, male students on the low end, a lot of male students on the middle end, a lot of male students on the high end, and the same will be true for female students, with a lot of female students on the low end, a lot of female students in the middle end, and a lot of female students in the high end. So if gender is interdispersed through GPA in the population and it's all mixed up, then we shouldn't really observe differences in our group samples because they're drawn from the same distribution of folks. We may observe, though, that group 1 performs a little bit worse than group 2 simply because by randomly selecting individuals, we ended up getting a few men who performed on the lower end of that population distribution in group 1 and a few women who performed on a higher end of that population distribution in group 2. But once again, if they're drawn from the same population, we wouldn't really expect to see a difference of means between group 1 and group 2 unless through random chance or statistical sampling error. Contrast that with our second figure, where maybe in reality, men do perform worse academically than women or female students. So here we're seeing that we are pulling group 1, sort of the male students with the lower GPA, out of a population where men are clustered at a lower level for GPA than female students. So here you can see that if we had a distribution of sort of male students on the low end, female students on the high end, of course our sample is going to reflect that difference because there's a real difference in the population when it comes to male and female GPA performance. Now, there is one caveat for this kind of thinking about difference of means tests, and that is we don't really know what the population is when we're collecting our data. So all we have to go on are our statistics calculated for independent samples. That is, we're going to have for group 1 a mean, we're going to have for group 2 a mean, but we're also going to have measures of the dispersion, so we can calculate the standard deviation for group 1, the standard deviation of group 2, and of course we can know how many people are in group 1 and how many people are in group 2. So the way we're going to figure out whether or not these groups are drawn from the same population is by comparing the means and comparing the variation in group 1 and group 2. So I'm going to illustrate that kind of crudely on my iPad here. So let's say I've got a number line down here and I've got two groups. And let's say that the mean for group 1, which will be the red group, is going to be 6. And the mean for the blue group is going to be 8. All right, so I've got my red group mean at 6. I've got my blue group mean at 8. And I'm going to draw a couple distributions on top just to illustrate how the logic of independent sample difference of means testing works. So let's say that this is the distribution of values for my first group, my group 1, my red group. And this is the sort of dispersion for my blue group, or my second group. Keep in mind that we're a little crude here in the illustration. So if you kind of look at the peaks where our means are, then the difference of means is going to be the first mean, the mean of the red group, minus the mean of the second group. And you can see that difference is illustrated in our graphic by that black bar. Now, keep in mind that there's going to be some overlap. That is, the high performers of group 1 will overlap with some of the low performers of group 2. And we're kind of comparing these two elements here. We're kind of comparing how much variation overlap there is between group 1 and group 2 to that overall difference. So if you kind of think about t-scores, we're looking at the variation vis-a-vis the difference of means for one sample difference of means test. And the same kind of rules apply. So we're comparing that variation in the sort of overlap between those two groups to how big the difference is between those means on top. Now, kind of look at this figure and you can see that there's a little bit of overlap, but for the most part, those peaks are very different. Now, let's contrast this to a different figure with the same means, but slightly different sort of standard deviations or variance. All right, so I'm going to keep the same distribution for the first group, and I'm going to draw a slightly different sort of figure for our second group, our blue group. Here you can see, once again, the means are drawn to kind of be the same, and what's really changed is the variation in group 2. So if we kind of look at the difference of means, we can see that x bar minus x2 is still given by this black bar on top. But when I start shading in kind of the green area, you can see that there's a lot more overlap because the blue values really stretch further into the distribution of kind of the first group and the red group. So you can kind of see in this figure that the difference between the means is a lot smaller than the shared variation between the two groups. So once again, you kind of compare these two figures, you get a sense of how difference of means testing works by using both the mean values from the groups, but also their variation to see that overlap and whether or not the difference between the groups is bigger than the overlap that the groups share. So let's finally work our way through a calculation. So here I have, once again using the SAT data, I've split Pennsylvania schools into two groups. Group 1 is non-charter schools in Pennsylvania, and Group 2 is charter schools in Pennsylvania. And here I have X bar 1, the mean SAT score for non-charter schools at 977. The mean score for charter schools is 844. The standard deviation for non-charter schools 101. The standard deviation of charter schools at 126. I've got 595 non-charter schools and 51 charter schools in my two samples. Once again, these are the same data we use for the one sample difference of means test, simply broken down into non-charter versus charter schools. So what you can see next is the calculation of t. Once again, very similar to the calculation we had for one sample difference of mean test, where the numerator is the difference of means, so in this case x bar 1 minus x bar 2, and in the denominator we have the standard error of the mean, which is basically based off of the standard deviation of the samples, but note here that since I have two samples, their math is a little bit more complicated, but it's just a matter of plugging in the values from above. So if we plug in our values, we have 977 minus 844 in the numerator, and then we've got the 101, the 126, the 595, and the 51 in the denominator. Going just through the mathematics and reduce that all down, we get a t-score of 7.34. Now, if we want to figure out whether or not that's statistically significantly different than 0, we have to go to our t-distribution table. Once again, we kind of already know that in a t-distribution table, the 95% confidence level is associated with the t-score of 2. That is, we need to be beyond positive 2 standard deviations from the mean of 0 or below 2 standard deviations from the mean of 0. In this case, we're at a 7.34, so without even looking at the table, we know that we can call these results statistically significant, which means that we would reject the null hypothesis that the means of group 1 and the mean of group 2 are the same, and conclude that, in this case, it looks like non-charter schools outperform in a statistically significant way SAT performance than charter schools.